Thank you so much for inviting me to give this talk. My name is Laura Domine. I recently moved from the US to Japan. I'm now a tenure track researcher in Tokyo at a national lab. And starting on April 1st, I will also be an assistant professor at Kyoto University. I will work through this talk in reverse. I will start by talking about local technosignatures, then scientific instrumentation, and then finish with AI foundation model development. So by local technosignatures, what I mean is technosignatures that are in or near Earth's atmosphere. And specifically, I am interested in technosignatures as a potential hypothesis for unidentified aerial phenomena. There are many hypotheses for these objects or phenomena that have been reported by credible witnesses over many decades, and that are reported to have characteristics that are outside the performance envelope of known objects. So those could be misidentified mundane objects, they could be man-made advanced technology, or rare atmospheric phenomena, such as ball lightning, which is another understudied area of research. In this talk, I'm interested in UAP and one of the potential hypotheses for their nature, which is technosignature. There is a long history in science of rare and dismissed atmospheric phenomena that ended up leading to major science discoveries. My favorite one is meteorites, which were dismissed as superstition until about 1800. And my colleague Wes Waters will talk about this in more details in his upcoming talk. Another example are transient luminous events, or sprites, which are colorful flashes of light above thunderclouds. Those were dismissed for a long time despite numerous pilot reports until they were first photographed in 1989. In the case of UAP, I'm interested in figuring out what the nature of UAP is, whether it is ball lightning or technosignature or something entirely different that we cannot imagine. So there is motivation for the scientific study of UAP. There is not scientific evidence. We look at worldwide numerous witness reports over many decades and sparse physical data. There are multiple government offices that for decades have studied the phenomenon, although not from a scientific perspective. For example, in France, GAPAN is located under the French Space Agency and has been in operation for 4 decades. In the US, their equivalent is now called ARROW, the All Domain Anomaly Resolution Office. And both of these offices have investigated thousands of cases. What's interesting is that the residuum of cases is, in both cases, about 1 to 3%. Those are cases that remain unexplained after thorough investigation and despite the availability of quality data. So again, this is not scientific evidence, but as scientists, it should motivate us to investigate. More recently, 3 years ago, NASA had an independent study about UAP, which confirmed that many credible witnesses have reported seeing these objects. Most are explainable, and then a small residuum cannot be immediately identified. And we simply do not have enough data to make a scientific conclusion about UAP, so NASA highlighted the need to have a data-driven framework in order to understand the nature of UAP. There are extra motivations which are not related to science for studying UAP, such as aerospace safety. The largest aerospace conference, AIAA, now has an annual UAP session. There are national security reasons to want to know what's in the airspace. And then from an outreach perspective, it is important to educate the general public about scientific approach. And given the large amount of interest in UAP, this is an opportunity to show how to approach the topic from a scientific perspective. The key question is, how do we move beyond investigating individual cases and adopt an approach that is data-driven? I am especially interested in instrumentation-based approaches to UAP. The goal is usually to figure out whether they are in or near Earth's atmosphere measurable phenomena that we can confidently classify as scientific anomalies. I will repeat that technosignature is one hypothesis, obviously not the only one, and that we must suspend judgment about the ultimate origin of UAP in order to conduct this study. There are multiple methods that are available to us. The main one I will focus in this talk is about developing multi-modal, multi-spectral instrumentation specifically to study UAP. Another way to study UAP would be to leverage existing missions and data archives in order to search for UAP signatures, and Wes will talk about this in his talk a little bit later. If we want to use instrumentation to study UAP, we could adopt one of two perspectives. One is to do exploratory research. That means thoroughly characterize the background and generate hypotheses from this survey. There are examples in science of such approaches. Those include biology efforts to catalog the genome, ethnographic fieldwork, and marine biology field studies. Alternatively, one could adopt a hypothesis-driven research, by which I mean design an experiment to pursue a specific signature. Whichever approach we take, we should have calibrated instrumentation and carefully validate it. So there is a growing number of efforts to design instrumentation in order to investigate UAP. There are two big categories of such systems. On the left-hand side, I am highlighting observatory class systems, such as the one developed by the Galileo Project at Harvard. Those are expensive, contain many instruments, which are meant to stay in one location for a long period of time in order to conduct a long-term census of all aerial phenomena over that one location. And over time, the goal would be to identify statistical outliers. There is a paper for which I put a QR code here, which explains the experimental design of this observatory class system, and I will go into a little bit more details in my next slides. On the right-hand side, this is another system which is being developed at Wellesley College by Wes Waters. These are portable and affordable observatories, which can scout locations potentially before installing a long-term observatory. So those two approaches are very complementary. I'm now going to focus on the large observatory class system and explain what the design is in the long term. After we calibrate and commission all instruments, the first step would be to perform a census of all aerial phenomena over the location. It will take a fair amount of time to validate that census data and to make sure that we understand everything in that background. We will have to find ways to categorize all the phenomena that comes up during that census and to quantify our uncertainties in that process. There may be statistical outliers that emerge over time, and those may or may not fall within the performance envelope of known phenomena. If we collect data for enough time, these outliers might become corroborated, in which case we may start to study them in a more focused and targeted way. We will be able to reject the ones that are within known performance envelope. And potentially, we will have instrumentation such as the one developed at Wellesley College to perform targeted follow-up observations. That means we would have generated a hypothesis that we can start to test. And we will share those results so that other scientists can corroborate independently. And whatever remains unexplained will have reached the stage of a scientific anomaly. If you would like more details about this approach, I encourage you to read the paper that is highlighted in the bottom right of my slide. Of course, every single instrument that is part of this approach will have to go through the usual phases of a scientific instrument, by which I mean calibration first and then commissioning phase. At each of these phases, we will be collecting calibration and commissioning data before we declare that we have science quality data that can be used for an actual science analysis. So the goal of all of these efforts at the moment is to achieve this last step of science quality data, which needs to be stable over time. Here is an example of the observatory class system, the Galileo Project observatory, and what instruments are included. The main focus is on optical instruments. So in the visible and infrared range, we have all sky cameras. There are also acoustic sensors, ADS-B receivers in order to collect aircraft information. We have environmental sensors. We are developing passive radar, and we also have a radio frequency spectrum analyzer. So each of these instruments are going in parallel through this pipeline of calibration and commissioning. This is because there are limited resources at the moment, and it is hard to do everything at the same time. So each instrument reaches science operation phase at different times, potentially. Once all the instruments are commissioned, the goal is to conduct commissioning for at least 1 year, during which we conduct an aerial census at the location to capture what the background is like in great detail. After that, we will declare that we are collecting science data and operate for many more years. At the moment, the only instrument that has reached the phase of commissioning is the infrared all-sky camera, which I highlighted in green here. In orange, I highlighted instruments that are still going through the commissioning and calibration process. So this is very much a work in progress. In this talk, I will be referring to data coming from this infrared all-sky camera, as well as acoustic sensors in the ADS-B receiver. Before moving on, I would like to explain what I mean by commissioning some of these instruments. For example, I will take the example of the infrared all-sky camera, which has 8 infrared cameras on a hemispherical dome that is custom designed and custom built. There are sunshades that occasionally mask the cameras to protect them from direct sun exposure, and the cameras are recording at different times of day. So the goal is to have continuous coverage, but in practice, not all cameras are recording 24/7. After the recording is done, we have machine learning algorithms that analyze the data and do detection and tracking of all objects passing through the field of view. So on the calibration front, we have done a lot of work to calibrate this camera. For example, I am putting here just one example. If you would like to see more, I encourage you to check the paper that I mentioned at the bottom of the slide. For extrinsic calibration, we used ADS-B aircraft. So each aircraft passing overhead is equipped with a transponder, which shares information about the aircraft type, position, and there is a timestamp. We collect these ourselves, and we also have access to historical database of such aircraft ADS-B data. We can use these in order to correlate the pixel location in the image to a 3D real-world location of the aircraft. And if we do that over time, then we become able to monitor the camera orientation over time and to make sure it is not accidentally moved. Once calibration is done, we've done extensive commissioning studies, and here is one example using aircraft again. We divided the aircraft into aircraft which are in range of the instruments, which are viewable, by which I mean in the field of view over the tree line, and then aircraft which are recorded, which happen to pass at a time during which a camera was recording, and then we have the category of aircraft which are detected by the machine learning algorithm. So every single aircraft is categorized into one of these 4 categories, and that allows us to define metrics for how the instrument is performing. We define efficiency as the fraction of aircraft recorded that are detected, and acceptance as the fraction of aircraft viewable that were recorded. So those teach you slightly different aspects about the instrumentation. And we measured those as a function of different atmospheric parameters, such as visibility or precipitation. And what you would expect intuitively is confirmed by these measurements. For example, efficiency increases as a function of visibility, and it decreases as a function of rain precipitation. We have done this study in order to map every area of the sky, which you see on the left-hand side, with an efficiency metric. So in the left-hand side, you have, for each camera, a 2D histogram, which shows you, each bin shows you what fraction of aircraft that were in range are eventually detected. And this metric is far from being uniform. As you can see, there are many factors that go into this calculation, and it is crucial to measure this metric, this efficiency of the instrumentation, in order to understand future data. On the right-hand side, I am showing how the fraction, the efficiency and acceptance metric vary as a function of distance to the instrument. As you would expect, efficiency goes down with the distance. The acceptance goes down overall as well. Finally, we used these commissioning studies in order to demonstrate how we would use this instrument once it is running alongside other instruments in order to look for outliers. So we would use machine learning in order to do detections and tracking of the objects. And the top middle shows you an example of detections in a 5-minute video. So every single dot here is a detection, and each color corresponds to a different trajectory. So if the dots are far away, then these are objects that were moving far or that were not detected properly. In the middle, I show that a lot of the trajectories are actually fragmented, so all of these algorithms need to be much improved. And on the right-hand side, I highlight that we conducted an example of toy outlier search. So we said, for example, if we were looking for objects, 2D objects with a sinuous trajectory, we would find about 144 objects which are ambiguous. Those are likely mundane, but we do not have other modalities or distance to elucidate these. And we did a statistical likelihood test to calculate how many of these outliers we would expect if we want to account for all of the uncertainties in our pipeline. And because everything is still in the preliminary stage, our upper limit was very large, which means we do not have much confidence at the moment in being able to identify potential outliers using this pipeline. So still a lot of work, but this is the pipeline that we expect for any instrument to follow before we can collect confident science data. So after we calibrate and commission each instrument, run for at least 1 year, 24/7, to thoroughly characterize the background, which collects a lot of data. Eventually, the goal is to start running with a trigger or a filter, which only stores events of interest. This would allow us to only store data amounts that are practical for long-term operation. And in this process, there are multiple questions that we need to solve. For example, how do we avoid biasing our survey because we have prior expectations of what phenomena we're going to find, such as aircraft, drones, birds, and so on. The other question is, how do we reduce this data amount while keeping an exploratory research approach? So we don't want to switch necessarily to a specific signature search. We still want to be exploring different hypotheses, but we need to reduce the data amount. So to answer these challenges, we turn to machine learning. These challenges are not unique to UAP-specific instrumentation. There are other fields, obviously, that collect large data sets over time from multiple modalities, not always aligned with each other, and where it's very difficult to generate annotations by hand. And when you're looking for outliers or novel classes of objects, it's a needle in a haystack problem. So nowadays, a lot of fields are looking at what is called foundation models. So this is a little bit of jargon word that was coined by Stanford researchers in 2021. Foundation model refers to an AI model that is pre-trained on a very large unlabeled dataset. For example, in the case of ChatGPT, it is pre-trained on a large fraction of the internet. Then it is pre-trained using self-supervised learning. So, for example, if you're working with text, like ChatGPT does, self-supervised learning means you remove some parts of the data or you transform them and then ask the model to predict or extrapolate what's missing. That's one example of how you can do this. And finally, an important characteristic of these models is that they are general purpose, which means they can be used after this pre-training for a variety of downstream tasks with little to no extra training called fine-tuning. So for example, ChatGPT, after it has been pre-trained, can do a wide variety of tasks from language translation to summary to fact-checking and so on. So the idea would be to create such a foundation model for multi-sensor, multi-modal data sets. So we would be collecting a large data set from our field stations and then conducting a self-supervised pre-training. So we would transform the data, and how we transform it will depend on the modality. This process of self-supervised pre-training will force the model to learn a representation of the data, so a compressed representation of the data, which is invariant to these transformations. And in the future, the goal would be to use this model for diverse tasks, such as object detection, classification, tracking, novel class discovery, which means finding out after the training that there is a completely new class of objects that were never seen during training, and outlier detection. One of the popular methods to train these models is called DINO, which stands for self-distillation with no labels. The way it works is you take your data and transform it in two different ways. And then you have one network called the teacher, one network called the student, and your goal is to have the two networks' outputs probability distributions which match each other. So if you do this process over a large enough amount of data, the hope is that it will learn features of the data which are useful for many different tasks. So I conducted with collaborators a proof of concept using 1 to 3 months of data from one of these Galileo Project observatories. The data was cut down into clips of 1 to 3 seconds. For the modalities, we used infrared videos and acoustic recordings. The videos come from cameras that have a field of view of about 50 degrees, and the acoustic recordings are in the audible range from an omnidirectional microphone. We use aircraft data from ADS-B in order to label snippets that are close to the closest point of approach of an aircraft. The machine learning model is taking input from the different sensors. So for example, acoustic and infrared. It is separately processing these different modalities, but there are also branches in the model that exchange information between the different modalities. And as the model processes, the idea is to combine gradually the information from different modalities before coming to a decision. So I have some qualitative results first, and then I will show some more quantitative results of this proof of concept. So this was trained without any labels, without any supervision. And here's an example on the left-hand side of infrared frames where there is an aircraft in the scene. The aircraft is circled in red, so it is that little white dot. And this was the input to the model, which was never seen before. And these are what are called attention maps. So these are layers, many layers from the model, where I have overlaid with the background image the layer parameters. And yellow means the parameter is high, which means the model is paying a lot of attention to that region of the image. And blue means it's not paying a lot of attention to that area of the image. So I have circled in red the layers where the model is paying attention to the aircraft, as you can see from the yellow pixel. So without having ever taught the model what an aircraft was or that it could be of interest, it is starting to learn that this is an object in the scene and that it should pay attention to this. This is from the acoustic branch on the right-hand side. So we work with spectrograms where for aircraft, we have a characteristic interference pattern. The aircraft sound reflects on the ground, and our microphone is at a certain height in the air. So we tend to see these U-shaped pattern, which I have highlighted on the left-hand side. And then on the right-hand side is the attention map for that same spectrogram. And again, yellow means high attention. So you can see that the model is starting to pay attention to these patterns that are characteristic of an aircraft. We also looked at quantitative ways to evaluate how the model is doing. So on the left-hand side, we took the acoustic branch and we tried to use it to do clustering on the aircraft and see whether the resulting clustering correlates with any physical features of the aircraft. What we found was that it did correlate with some physical features. For example, the number of engines is a feature that the model seems to have learned and is able to separate reasonably well aircraft with one or two engines. And then the last task, the most important one for which we want to train this model, is generalized class discovery, which means figuring out that you're encountering a completely new class of objects that were never present during training time. So we started evaluating this model for generalized class discovery, and so far it seems promising. We use aircraft that we partition into known and unknown classes and try to see whether the model can understand that it is seeing a new class of aircraft. This foundation model is going to be important for UAP instrumentation-based investigations. The goal is to fine-tune it for other detectors, not just the Galileo Project observatories, and to use it for many tasks such as object detection, real-time trigger at the edge, and potentially generation of multimodal synthetic data. These are the key takeaways from my talk. I believe that I and many colleagues believe that multimodal, multi-spectral instrumentation will be key in order to advance investigations into the nature of UAP. Technosignature is one hypothesis, not the only one, and the work on this foundation model may enable unbiased aerial census. We are working to organize an annual UAP-focused academic workshop. If you're interested, please get in touch. And I want to highlight also that this is very interdisciplinary work. We need expertise from many different fields in order to establish that background in the aerial survey. And we hope to contribute back to other fields by developing methods for UAP studies such as the foundation models. Thank you.
Thank you very much, Laura. We have some time for questions. And I see a question from Andrew Fracknoy, who points out that by far the most competent and comprehensive investigator of documented UAP reports is Mick West. Is your team aware of his work, and will you include him and similar veteran skeptical investigators in your project to help eliminate cases that are not good subjects for the scientific community's efforts?
Yes, in fact, Mick West has regular communications with the Galileo Project, but I want to highlight that his work falls in the category of case investigation. And the goal of this effort is to move beyond case investigation and detective work into collecting science data in order to solve this mystery.
Okay, I have a question myself. What do you consider the biggest challenge
for this work?
Yeah.
I think there are two big challenges. One will be how to process all of the multimodal data that we collect for this purpose, which for which the foundation model is one answer, but it is not the only one. And then the stigma that this topic encounters and which has been hampering efforts to study the topic. I think those are the two most immediate challenges that we need to resolve.
Okay, thank you. There's a question from Joseph Lazio. Could you say a little more about your use of ADS-B? Specifically, what happens if an airplane without an operational ADS-B system flies over one of the Dalek infrared stations?
So ADS-B is extremely useful in order to conduct the commissioning process of these instruments because it provides us with a subset of the data which is labeled, which is hard to come by. It also enables us to establish the performance envelopes of aircraft. So if an aircraft was to fly overhead without ADS-B, its kinematics and features would fall within that phase space of aircraft that we determine using ADS-B.
Okay, are there any further questions? None coming in at the moment. There's one from Benjamin Fields. Fantastic talk. Interested in the point around hypothesis-driven versus agnostic approaches. Regarding the technosignature hypotheses, are there any predictions? What properties could a UAP observation have that would make ETI the top contending hypothesis? Don't be afraid to speculate here. Interesting to hear your answer.
Probably the first answer that most people would bring up is kinematics. So the first step will be to establish that there is indeed a phenomenon that is anomalous in the atmosphere, and that will be a huge amount of work. But beyond that, capturing kinematics that does not fall within performance envelope of known technology or known natural phenomena is probably one of the most straightforward ways to look for a technosignature signature.